I will start with a reminder of what we did last time. And where did we stop? Right. So we constructed a map. I think we called it phi from isomorphism classes of irreducible finite dimensional representations of semi-simple algebra G to what we called P plus. It's an intersection of weight lattice and the closure of positive Weyl chamber. And the construction was like that. We proved that every representation from here is a highest weight representation of highest weight, which is exactly from this set. And for such a representation, and this highest weight is unique. And for such representation, we put into correspondence weight lambda. And moreover, we proved that it is injective. So if you have, because we actually proved the following proposition, that if you have two representations of the same highest weight, then they are isomorphic. And the theorem that we were going for is that actually phi is bijective. So what is left to prove is surjectivity, that if I take any lambda from this set, then there exists finite dimensional or irreducible representation of this highest weight. And we made some progress in the proving of this theorem. We actually had the following construction. So we considered, we fixed some lambda from P plus. So such lambda are sometimes called dominant integral weights. So I will use this terminology from time to time. So fix this, then consider Fermat module with this highest weight. And we consider actually some special weight subspaces in this Fermat module, which are given by shifted action of Weyl group on lambda. Okay, so shifted action is, let's recall that we denoted by dot. It's W of lambda plus rho minus rho, where this is just usual action with these reflections and stuff. And SI here are simple reflections. Okay. So we actually claimed that this is one-dimensional, and if you have a vector here, then it is singular. So if you're looking for singular vectors inside Fermat modules, that's where you can find them. Maybe in some other places as well, but that's here for sure. Maybe, let us index these vectors corresponding to this index I here. So there are of them. And then we took Vi and generated everything out of these Vi's. So Mi is U of G applied to Vi. So this is another notation. So this is submodule in M lambda. And this is proper submodule because you never can get upstairs and get V lambda in here, right? So each of these modules are proper submodules. Actually, they are all, we never proved that, but it is easy to prove. I will not do this, maybe we will do it as an exercise. That each of these modules are also Fermat modules. So if you have a single vector in a Fermat module and generate everything out of this single vector, then you again have Fermat module, but maybe of some other highest weight. Okay. In this case, Mi is M Si dot lambda. Just to let you know, but we don't. Mi is a proper submodule of M lambda. We never say that it is actually Fermat is isomorphic to some Fermat module, not this one. So it's Fermat module which is submodule in this Fermat module. Okay. Yes. And then we would like to consider quotient and call it L lambda is the quotient of M lambda by sum of MI's. And we would like to see, so goal to see that L lambda tilde is, so dimension of L lambda tilde is less than infinity. So L lambda tilde is finite dimensional. And actually we explained last time why this would imply the theorem, this theorem that phi is bijective, right? Because if it's finite dimensional and it has highest weight lambda, then you actually can decompose it into irreducibles. This highest weight will be in one of irreducibles, and this irreducible, which actually it's not a secret, coincides with this L lambda tilde, but that's another exercise that you can do, is then a representation of highest weight lambda. Okay, so the main point to see that this is finite dimensional, and this is something new comparing to SLN. In SLN, you just could take and construct this representation L lambda by just construct them explicitly. Here we just have to use Fermat modules somehow. Okay, so let's try to prove that. So proof will need a few claims. So claim 1, actually 3 of them. We will need the following, and this is the most technical one. Let us consider some subset inside L lambda tilde. It is defined as follows. It's all vectors in L lambda tilde such that if you apply SL2 triple corresponding to a simple root for every simple root to V, then dimension of this is less than infinity. This is for every I from 1 to R. Okay. So these are all vectors that belong to finite dimensional subrepresentations of L lambda tilde. Finite dimensional with respect to SL2 triples. Okay. So that's our definition for L lambda int. Int stays for integrable. And it has something to do with actually lifting representations to the group. But, okay, that's why it's called integrable. So, all right. Then, so and what is the claim? So if I fix such thing, then L lambda tilde int is a submodule in L lambda tilde. So proof of claim 1. Okay, so let us take let us take a V from L tilde lambda integrable and X some element of G. So I would like to see that if I act by X on V, I'm still in here, right? Okay. Therefore, I need to find some representation of SL2 alpha I for each I, such that X finite dimensional, and that is inside here, such that XV is in this finite dimensional representation. All right, so let us fix some I from 1 to R. So let's fix a simple root. Then let me consider V to be everything which is generated by SL2 alpha I from V. By definition of L lambda integrable, dimension of this is less than infinity, right? So V is inside here, and we just by definition, then it means that dimension of such thing is less than infinity.
The space V doesn't depend on the choice of
It does. I is here.
So you have a bunch of
Yes, so I would like this to, I'm fixing something, right? But this can be done for any I from 1 to R, right? So this condition is actually for any, right? So I'm just doing proofs for some fixed one, then you can repeat the same thing for any, and this will work, right? Okay, so a dimension of this is less than infinity. Then let me now consider the space GV. Right? This is, well, it's clear what it is. Right? It's just all U in L tilde lambda, right? Such that U is X applied to some U tilde, right? Where X is from G. Not I'm stressing not from U of G, but from G. Okay, that's important here. And U tilde is from V. But this is also finite dimensional, right? Because V is finite dimensional and G is finite dimensional. It's just our semi-simple Lie algebra. Of course, this thing is just spanned by everything, like basis from element of basis from here, X on element of basis from here. There are finite number of such elements. All right. Then, of course, XV is inside GV. Right? So X from here, V from here. So by definition, this is. And then I also claim that GV is SL2 alpha I module. So because, okay, let us check this. So indeed, let's take Y to be from SL2 alpha I, and some vector from GV. Any vector from GV is of this sort, X times U tilde, right? So I am taking this one is not really good because I fixed X, right? So let me change in here to maybe Z, right? Since I already fixed X. So let me take Y from here and then Z from G, U tilde from V. Then I apply Y to some general element of GV, which is Z U tilde. Then I do what? I commute. I pull Y through Z to the right. I'll have Z Y U tilde. Right. Then Y U tilde, it is in V. This belongs to V. Why? Because U tilde is from V, right? And V is a representation of SL2 alpha I. And we take Y from alpha I. So we never go outside of V if we apply something from SL2 alpha I. Right? So this is in V. So therefore, and Z is in G. So therefore, the whole thing is in GV. This is done. Plus, we need commutator. So I have commutator of Y and Z, U tilde. Commutator is also an element in G. So it's an element in G times an element in V, again in GV. So the whole thing lives in GV. So therefore, if I apply an element Y from SL2 alpha I don't go outside of GV. So GV is SL2 alpha I module. And X, and moreover, it is finite dimensional, right? So XV lives in some finite dimensional SL2 alpha I module. And actually, this is for arbitrary I from 1 to R, right? And this means then that XV is inside L integrable tilde lambda. So the claim is proved. Claim 1 is proved. Okay, so this was the most technical part. Now, claim 2 is that L lambda tilde integrable coincides with L lambda tilde. proof of claim 2 is just one line. I argue that v lambda tilde. So this is image of highest weight in m lambda in L lambda tilde, right? So I take highest weight in m lambda, take the quotient. What is left, I denote by v lambda tilde. Okay, image of this in here. I claim that this belongs to L lambda tilde integrable. That it actually lives in finite dimensional representations of SL2 alpha I for each I. This is why. This is just because, so I take some I and start applying it to v lambda tilde. Okay? Then what happens? I cannot go upstairs because v lambda is highest weight vector, right? So I generate something by f's from v lambda. So to make it, so I would like this something to be finite dimensional too. So I would like at some point to have 0. But this is provided by this quotient. So what is vi? So remember, mi was u of g vi. And vi lived in some weight subspace of m s dot lambda, right? But why it lived there? So at the end of the previous seminar, we actually discussed it. Because it is actually, so vi, you take f, I, and apply to v lambda. But how many times? Lambda I plus 1 time. So where lambda I is the weight of v lambda, actually weight, let me try it like this. Lambda I is the SL2 alpha I weight of v lambda. Lambda I is the SL2 alpha I weight of v lambda. So that's what was going on. So you actually take this v lambda and generate Verma module out of it. But because lambda lives in P+, you can actually find Verma submodule for SL2 and quotient by it, and obtain finite dimensional SL2 alpha I model. So that's exactly what's the point of our construction, right? So therefore v lambda, and this can be done for any I. So therefore v lambda, if we try to go by f's for any SL2 alpha I, we will hit 0 at some point, at this point. Right? So that was exactly the point of this construction. And v lambda, therefore, by definition, is in L lambda integrable. But L lambda integrable is a submodule in here. And this one actually is generated by v lambda. Okay? So, right. So we take v lambda tilde and take u of g. On one hand, this is L lambda tilde, right? But on the other hand, since L lambda integrable tilde is a submodule, then U of G, V lambda, is inside. Right? Well, just because if you have submodule, you take a vector in this submodule, start acting by G, by U of G. You will never go outside of the submodule. That's just by definition of it, of being submodule, right? So this is inside, but this is inside L lambda tilde, which is U of G d lambda. So we sandwich it, and we see that L lambda integrable is exactly L tilde lambda.
Maybe something not tilde.
Say it again.
Is V lambda tilde is the image of the V lambda.
Yes, so maybe here we also need tildes. Yes. Okay, clear? Not clear? Abner? 50-50?
Because you have to read some.
Okay, okay. But at least statements, they're clear. Okay. So what might be, should be read, right, and go back is that actually how we constructed these FIs. Right? So they're exactly like this. You just, at some point, so we're using Verma modules for SL2. And we can kill something in this Verma module and get finite dimensional. And this is exactly what we want in L lambda. Which ones?
That F sub I, how it's defined B sub I.
These ones?
It's the F that is in the copy of SL2, right?
Yes.
Okay.
Yes. So this is SL2 triple, right, corresponding to the root alpha I. And Fi is F in this SL2. All right. And then claim 3 is that actually for any element of Weyl model, of Weyl group, dimension of L lambda of mu, L lambda tilde, is the same as dimension of L lambda of W of mu. Tilde here as well. So this proof of this similar to the proof that we had of the similar statement in finite dimensional case. Actually, this proof you should remember because I said it wrong first and then I corrected it. So remember this one, this proposition. Okay. So what was going on there? So if we had finite dimensional representation, right, instead of L lambda, if I have any finite dimensional representation, then this is true. That was our proposition. How did we prove it? The only thing that we needed is that it is finite dimensional for each SL2 alpha I. And then I used this symmetry for finite dimensional of SL2 alpha for SL2, right? Symmetry with respect to 0. So symmetry with respect to 0 is exactly simple reflection if we translate it to here, right? So the only thing that I need to claim such a statement for some representation V in here is that in this representation each weight vector is actually a vector in some finite dimensional submodel of SL2 alpha I. That's the only thing that we used in this proof. And we have it by claim 2. We have it. So, all right. And we're almost there. So continue with our goal, with the proof of theorem. That is, we would like to prove that dimension of L lambda tilde is less than infinity. So what do we have? We have, so denote the set of all weights of L lambda tilde by P lambda, L lambda tilde. Okay, so this is all mu in H star such that L lambda tilde of mu is not 0. Then we actually proved that P L lambda tilde is disjoint union over some OI, where OI are orbits of respect to action of Weyl group. So where OI are orbits with respect to action of Weyl group, right? Because of this, right? We have so if I have one weight, then I reflect that it also will be a weight, and so on. So all weights come and forms like orbits of Weyl group. This is by claim 3. Okay, and this means that actually we can write for this set P L lambda tilde that it is disjoint union of W mu. So this is the whole Weyl group. So this is like an orbit corresponding to the point mu, right? Where mu actually runs over P plus, right? This is just because each orbit of Weyl group has exactly one representative in P plus. So if I have orbit, then I have exactly one representative in P plus. So I take OI, choose this representative, call it mu, and form everything by action of Weyl group. Then choose another orbit, do the same, and this is the decomposition. Okay? Very well. So Weyl group is finite. So this is finite, right? And but this is, I can actually write P plus intersect, so and I actually can write here mu less or equal than lambda, right? Well, just because all weights in Fermat modules, they are less or equal than lambda. But then some of you and we together on a seminar proved that actually this set is finite. Okay, so if I take something in P plus and consider everything that is less, all elements of weight lattice which is less, which is obtained by subtracting roots with positive integer coefficients, this set will be finite. Okay, so this is finite. Each of this is finite. So therefore, P of L lambda tilde is finite. The only thing which is left to see is that each weight subspace of m lambda, L lambda tilde is finite dimensional. Right, so L lambda tilde has finite set of weights. If each weight subspace is finite dimensional, right? Also, L lambda tilde, of course, has weight decomposition. So if each weight subspace is finite dimensional, then we are done. L lambda tilde is finite dimensional. But okay, why each weight subspace of L lambda tilde is finite dimensional? Remember what was L lambda tilde? It's a quotient of Fermat module, right? What do we know about Fermat module? About its weight subspaces? It's finite dimensional. It's again was one of the problems from the previous list. Okay, and we actually did prove it. So. So okay, this follows from m lambda, the dimension of m lambda mu is less than infinity for each mu. So we are done, right? Since L lambda tilde is direct sum over L lambda tilde mu, where so over mu in p lambda in p of L lambda tilde. So this is finite. This is finite dimensional. So therefore, dimension of L lambda tilde is less than infinity. That's it. Yes.
That L tilde lambda int block.
Say it again, sorry.
What do you mean with that notation? Claim 2. Yes, claim 2.
Claim 2.
Yes. What do you mean with
This?
Yes.
They just coincide.
I mean, in this part, you never use that factor.
No, I used that to prove claim 3. So this actually means that every vector of L lambda belongs to finite dimensional representation, of SL2 alpha I. And that I need for claim 3. So claim 3 follows from claim 2. But claim 3 I need in here. Okay. All right. So therefore, we are done, and we are done with classification of all reducible representations, finite dimensional, of semi-simple algebras. Okay. So now we would like to discuss characters. So characters gives us a way to decompose representations into irreducibles. So it's an important instrument, and we know already what are characters from the first semester. So let us now generalize it to the setting of all semi-simple algebras. All right. So characters.
L sub lambda tilde is the quotient of what is this second? Like what is the?
What is this?
It's m sub I. No. The upper in the quotient.
In the quotient. This is mi. Well, yes. So this is sum over mi's. Yes. very well. So what are characters? Of representations. So we would like to consider the following set. Let me denote it like this. And this set consists of finite sums, like formal sums, I should add, of the form like this. So it's sum a lambda, and this is some formal symbol. You should understand this. In some setting, it can be just real exponential map, but for now, for us, it's just formal symbol. This lambda runs over a star, but I say that it is finite, so only a finite number of a lambdas are not zeros, and the a lambdas are just complex numbers. So you can actually, so elements of C of H star can be added and multiplied. So it's actually an algebra. Can be added and multiplied. So you add it like like polynomials, like some linear expressions in E lambda, right? And if you multiply it, if we set, if you take E lambda and multiply it by E mu, these two formal symbols, this is E lambda plus mu. Yes, they just multiplied as exponentials. Okay. So this is our rule of multiplying E lambda and E mu, and this rule is extended by linearity to all sums like that. Then you can multiply them, and you add them just term-wise. Right. So mathematicians call that such thing as a group algebra. So you look at H star as as a group, abelian group, right? Then such a thing is called group algebra.
But also can be not commutative, not abelian.
Yes, it can be not abelian, but yes. So it's abelian because we have plus in here. But for some other group, it might be a difference between this one and this one. But still, you can multiply series, right? It's just matters in which order. Yeah. So you know something about group algebra, right? Yeah. Okay. But we need actually extension of this. So let me denote it like this with a hat.
I'm sorry. Is the sum finite, or like what exactly it does?
It is finite. It's written finite formal sums.
Yeah.
It
is not exactly clear what it means that the sum is over elements in the dual to Cartan's logic.
Why not? So you have formal symbols which are labeled by elements from here, and you consider finite sums like that. So each term is a complex number times some symbol like that, and you consider finite sum of this.
It is not clear how is the sum defined. For example, in the case when two elements of eta star are proportional one to another? Like, do we have a rule of how we do how we add?
So if you have lambda and c lambda,
Yeah.
so these are two different elements. Then this is two different elements. So then this is just this.
Uh-huh.
You don't.
There is no.
No.
Uh-huh.
Yes. Right. So we look at this as an abelian group, and for each element of this group, e to the lambda is a different element. So this it's a huge amount of this e to the lambdas.
It's like, is it true that e to the power of lambda to the power of c equals e to the power of c lambda? Like, is this a real experiment?
Yes, if c is integer, natural number. Well, and actually if it's rational as well, yes. For some complex, it's not clear what to take. Because, well, in algebra, you can multiply in algebra. That's the only thing that you can do, right? So if you take e to the lambda times e to the lambda, then by our definition, it's e to the lambda plus lambda. So it's e to the 2 lambda. In this case, yes, it is. And for each natural, it is consistent. Just because you have this rule. And of course, you can say that e to the 0 multiplied by every e to the lambda is e to the lambda. Well, you can play with it, and you see that so it's also consistent with. So you have inverse elements.
So
if you took minus here.
Algebra with the unit clearly
Yes.
generated by
Yes.
the elements of eta star.
No, yes. If you. Yes.
Yeah.
So it's labeled. It's labeled by. So this is the definition. Okay. So, but of course, something is consistent up until the point where you just don't know what to take. So you don't know what does it mean to take into complex power. So rational power maybe, because you have some kind of inversible elements here. But in general, group algebra you might not have. All right. So, but we need more than that actually, and we have then. I would like to consider finite sums of series of the form sum e a to the mu e to the mu less or equal than lambda for some lambda. So I extend this like that. So this is subset in here. And so I just would like to include infinite dimensional representations of highest weight in here. Suppose, so definition, suppose that V is a okay, so it's a direct sum, finite direct sum of representations of highest weight. In this generality, we can define character of V to be sum over lambda in H star dimension of V of lambda e to the lambda. So this is an element in C of H star. C of H star hat. So this is what it means to have character. So we have symbols like that, and coefficients are dimensions of corresponding weight subspaces. All right. So let us consider a first example. Yes. So proposition character of m lambda is given by the following: e to the lambda divided by the product of 1 minus e to the negative alpha as alpha runs over all positive roots. So here you should understand really such a fraction as a series that goes like that: 1 plus e to the negative alpha plus e to the negative 2 alpha, and so on. Okay. Let us prove that, but it's actually obvious that when it's like that. Yes.
The formula for the character of Lemma was
E to the, sorry, yes. Lambda here should be like that. So the proof is like that. You just need to see what is 1 over denominator here. Right, so 1 over denominator alpha in R plus 1 minus e to the negative alpha. Well, we can just, expand it and stare at it for a while and see that it works like as needed, right? It's some combinatorics. So it's one factor. The first factor here is like that. So e to the negative alpha 1, e to the negative 2 alpha 1, and so on. Second factor is 1 plus e to the negative alpha 2 plus e to the negative alpha 2 alpha 2, and so on. And then you continue, and then you have the last is 1 to the negative alpha, I don't know, k, plus e to the negative 2 alpha k, and so on. So factors like that. And then this equals to expression like this: 1 plus sum, then with some coefficients e to the negative alpha, where alpha are what's called belong to positive subset of root lattice. So Q plus here is just sum, is all elements of H star R of the form n I, or maybe mi, alpha I from 1 to k, where mi are from like this. So actually here, alpha 1, usually we denote alpha 1 to alpha r all simple roots, but here I mean that alpha 1 to alpha k are all positive roots. So some subset of them are simple, but you have more positive roots than just simple. So these are positive roots. Very well. But so here, n alphas, it's easy to see what is n alpha. It's just a number of ways to write alpha as a sum mi alpha I from 1 to k. Right? So you pick some alpha from Q plus. There are different, since positive roots, they are more than dimension of H star R. Then there are different ways how you can write like a given root in such form. Right? And then just, looking at this, how do you write, how do you choose how to write it? Okay, you pick one term from each factor here, okay, in such a way that exponents in these exponentials, some of them will give you this root, okay. So I take so all yes. So I think I kind of said everything, right? So the possible ways how I can choose one term from each factor such that the corresponding sum is my alpha is exactly the coefficient for e to the negative alpha in this expression. All right. And actually, this proves everything, because this is the same as dimension of m lambda mu. Right? So what do? You take highest weight vector and apply f's. Right? What is the dimension of given weight in Fermat module? Just because of PBW theorem, Fermat module is isomorphic the vector space to u of n minus, right? So actually, number of ways how you can get to this weight by applying negative roots, right, is actually, but you cannot, so if you permute like alpha 1 plus alpha 2 is the same as alpha 2 plus alpha 1. That's exactly what PBW theorem actually says to you, right? So anyways, so dimension of weight subspace in Fermat module is exactly in how many ways you can write mu, right? So this is exactly, I'm sorry, what is this mu? Maybe this I also should write, right? So I actually should write lambda minus alpha, right? Because this alpha here, yes, like that. That's it. So again, I'm kind of forgetting for numerator first, right? And working with denominator. I'm forgetting about numerator because it just shift, because the picture is just similar for all highest weights, right? And this is just to shift this picture to the weight that I need, okay? So what is important is that how much I go from highest weight to the weight I need, so this alpha, all right? And but this, how I can write this alpha as a sum of positive roots is exactly the dimension of the Fermat module. And this is exactly by this simple combinatorics exactly the coefficient in this expression for this fraction. And this proves everything. All right. So first example we saw. Okay. So today I would like to show also Weyl's dimension formula. We saw it for like maybe on the last lecture we saw it for SLN. But before that, let us see how exactly characters can help us in representation theory. For that, I need a couple more technicalities. In particular, I need C of P. I'm kind of restricting C of H star a little bit. So these are now finite sums of the form sum over lambda in P, a lambda e to the lambda. Okay, so now I'm saying that lambda can only be in weight lattice here. All right. Then, obviously, Weyl group acts on C of P. Right? Because if you have something from weight lattice, apply to Weyl group, it will be still in weight lattice. Okay. All right. Because by definition, weight lattice is something which, when you take this, something, some expression with the form that you have, then it's integer, right? That was the definition of P. But this form is invariant with respect to action of Weyl group. So therefore, if I apply Weyl group, it's still in weight lattice. Okay, so that's a quick explanation why W acts on C of P. And well, what the action is like that. W, like explicitly, I'm saying that it is like that. If I take an element in the Weyl group, apply it to such sum, it means that I have sum A of lambda e to the W of lambda. What I said before is that W of lambda is also in P if lambda is in P. Okay. So it's still an element in here. Okay. And let us denote C of PW the elements which are invariant with respect to action of Weyl group. So elements invariant with respect to action of W. So it means that if I take this element, apply any element of a Weyl group, then it doesn't change. Okay. Elements invariant with respect to action of W. Okay. And proposition that I need is that characters of finite dimensional irreducible representations of highest weight lambda, well, as lambda runs over all dominant integral weights, is a basis in C of PW. Let's prove this. we can take some obvious basis, which is sometimes in literature called orbit functions. So these are, let's denote them as m lambda. So m lambda is sum over elements of Weyl group e to the w lambda. So as lambda in P plus. So this is obviously a basis in C of P w, right? Well, because like if you take anything from CPW, right, it is decomposed into sums over orbits of Weyl group, right? So if you have some term that sits, if you have some term in it, right, then you have all the terms that are obtained by an action of Weyl group, okay? Just because it's invariant, all other terms should be there for sure, okay? But then each such orbit should have some term e to the lambda, where lambda is in P plus, right? Because again, each orbit has a unique representative in P plus, and that's exactly it. So you kind of break down your element C of PW into such sums. Each such sum has term e to the lambda, where lambda in P plus, and then the rest is given by an action of Weyl group.
So the dimension of these CPW is just the lambda P.
Its dimension is infinite. So P plus is infinite set. Yes. Yes. So, but then also we can take character of L lambda, and of course it has the highest weight subspace, which is one-dimensional, right? This is our V lambda from which we generate everything, right? And so therefore you can take this highest weight lambda and consider the orbit function corresponding to this lambda, m lambda, right? Then every other weights will be in P plus, will be smaller than lambda. But they also come with the whole orbit, right? So we can write it like this. And times maybe some maybe some coefficients, I don't know. But here coefficient is 1, right? Because dimension of V lambda lambda is 1, dimension of the highest weight subspace. There's only one highest weight vector, because L lambda is reducible. Okay, but this means that transformation from this, this means that the characters of L lambda are written in terms of this basis using some upper triangular matrix. It's of course infinite, right? And you don't have well, if you just order all like so it's written as an upper triangular matrix with ones on diagonal. So it's like semi-infinite matrix, but still it's okay. You can still invert it. Okay, but technically, what does it mean to invert like semi-infinite matrix, upper triangle with ones? It's just recursively express. So of course you can take M0, right? And you can take so for each, so you have a bunch of elements such that character actually is the same as m lambda, right? It is a base of your recursion, right? But then, so suppose, so what I'm trying to say is that from 1, it follows that we can express m lambda from characters of L lambda as follows. So you have m lambda is character of L lambda plus sum over mu less than lambda characters of L mu times some coefficients c mu tilde. So that's the statement. Okay, it is it's almost an obvious statement if you think about it. So you just need to say the following. So suppose you can fix some lambda, right? Suppose that you can express all m mu in terms of characters of L lambda like this for all mu less than lambda. Then you can express for lambda as well from just using 1, right? So to start this process and to express all characters of L lambda, you just need to check the base. You just need to check that so this claim, let's call it star, follows by recursion, and the base, need to check the base. And base is the following. You just take lambda in P plus such that there is no mu less than lambda, which are also in P plus. You just need to take all this, okay, all such lambdas. And for such lambda, we just need L lambda is m lambda. But this one is easy because, like, so suppose you take highest weight vector in P plus, right? And this just means that if you apply Fi's, you go outside of P plus, right? So there is only one weight for this representation in P plus. And the rest are given by just applying Weyl group because the weights of finite dimensional representations are symmetric with respect to action of Weyl group. Okay, and that's exactly gives you that L lambda is m lambda, and there's no others. Okay, so base is checked like that, and then recursively you take L lambda. You know that for smaller you can express, therefore you can express for this one, and so on, and so on, and so on. So therefore you can you have this, call it 2, and you have this, call it 1. So from 1, we know that, let's call this set B, is linearly independent. And from 2, since M is basis, and but you can obtain all M's just from characters, B spans C P of W. So therefore we prove that this is a basis. Okay, so let me introduce. I'm kind of tired of writing character of L lambda. So we proved. So we just let me denote this as high lambda. Okay. So the next statement that I will need, proposition. Suppose that I have product of two is written as a linear combination of n nus, where nu is from some p plus. And nu can be 0. Actually, it will be 0 for infinitely many nus, and non-zero for only finite many. What I claim is that this is equivalent to fix a lambda and mu in p plus here, and suppose it's written like that. This is equivalent to L lambda tensor L mu is a direct sum of n nu L nu as nu from p plus. So this notation is just that you have n new copies of L nu. So direct sum of L new copies of n nu. So this is n nu L nu, and then direct sum over other nus. Proof. Easy direction is this one. They're all easy, but this one is easier. I just follow. This one just follows from the definition of characters. Right, so actually follows from multiplication in C of P, definition of characters and the following consideration. So actually, if you take L lambda tensor L mu and consider its weight subspace, I don't know, nu, then it is given as a direct sum of L nu, so L lambda nu 1 tensor L lambda L mu nu 2, where nu 1 plus nu 2 equals nu. Right? But this is exactly how coefficients in this formal sums multiplied. Right? It's similar formula. All right, so you just right? So actually from this, like dimension of this, which is yes, so I kind of break this down into term-wise, right? Is dimension of, so maybe I can continue, right? So that dimension of L lambda tensor L mu nu is the dimension of L lambda nu 1 times the dimension of L mu nu 2, and I need to write here sum over nu 1 plus nu 2 equals to nu. Right? This is one thing, and the other one, well, if you have okay, let me write it down explicitly then. So high lambda is the sum dimension, just to recall, L lambda mu e to the maybe nu 1, say here. And high mu is the same, you just change nu 1 to nu 2, dimension L mu nu 2 e to the nu 2. And then high lambda high mu then is sum over nu, and if you multiply these two series, the coefficient for e to the nu will be exactly sum dimension, maybe I need more space here, sum e to the nu dimension nu 1 plus nu 2 equals nu L lambda of nu 1 times dimension of L mu nu 2. Right? So if you write like this, multiply, coefficient will be exactly this as we computed. Right? So, but these are coefficients, so we can actually high L lambda tensor L mu is sum dimension L lambda tensor L mu nu e to the nu. And we check that this equals to this. Right, just term-wise. So this equals to this. So therefore, if I have therefore, if I have this decomposition, right, characters of this and this coincide. Character of this is he lambda he mu, and character of this is sum of n nu he nu. Right? So therefore, we check that from here to here we are done. And another direction right? Okay, so maybe let me write this down, right? That I just said. So we know that. So therefore, we know that he lambda he mu is he L lambda tensor L mu. Right? It is character of L lambda tensor L mu. This we check here. On the other hand, character of sum of n nu L nu is just sum of characters. Just sum this term-wise, right? Because dimensions. So your weight subspaces, they just added, and dimensions just added. So coefficients just added, right? So this is sum over high nu with coefficients nu. And since this one is isomorphic to this one, it means that high lambda, high mu is n nu sum over nu n nu high nu. Very well. So okay, now the other direction. So suppose right. So the other direction is this one, right? So suppose that I have such a decomposition of characters, and suppose then that that I have also some decomposition with maybe some other coefficients m nu, L nu. Okay, so suppose that we have this, and also we have such a decomposition of characters. I need to check, so we need to show that n nu equals to m nu, right? But from here, as we showed before, so I don't know, let's call it star, it follows that high nu, high lambda times high mu equals sum m nu high nu over nu, right? This is exactly what we showed in the first. But also we know that we have the similar decomposition with n nu here. But since highs form a basis, right? So since high nu form a basis, in CPW, this coefficient just should coincide. So n nu equals to m nu. So now we know that, okay, if I have tensor product, I can decompose it using characters. And if I have just some character, some representation for which I can define character, if I can just find its character, decompose it in the basis of characters of reducible representations, and this will be exactly decomposition of this given representation to the reducibles. Okay, so it's one-to-one correspondence. Okay. So the last thing that I would like to do today is just to present you the Weyl's character formula and maybe at least mention briefly why is it true. So Weyl's character formula so for each lambda from P plus, we have that character of finite dimensional reducible representation of highest weight lambda is given by the following formula. It's sum over Weyl group, and then I have some sign that I'm going to define in a minute. It depends on the element. Then e to the w dot lambda. So this is shifted Weyl group action that we mentioned before, divided by the denominator that we already seen today, product over alpha from R plus 1 minus e to the negative alpha. Where again, this I should understand like as this series. What is L of W? So where L of W is what is called length of an element W. So it is minimal natural number, actually, I should say non-negative integer, because it can be 0 as well. There's only one element, which is identity, right, in the Weyl group. Such that W can be written as a product of simple reflections. Okay, so for example, if I have simple reflection, L of Si is 1, L of identity is 0. And there's actually a maximal element, element of maximal length, which is some statement. It's not that obvious. And the maximal possible length is actually the number of roots over 2. Okay. Okay. So how one proves that? So okay, we actually for 3 people in the last lecture of previous semester, we actually proved that for SLN. So for SLN, it's already kind of non-trivial thing to do. All right. So what did we do? We presented. We want this as to be decomposed as a sum of Fermat modules somehow, as the characters of sum of characters of Fermat modules. So that's an idea. And you see this denominator here comes exactly from this idea. All right. So in general setting, we actually can generalize what we did last semester. So we actually used like Harris-Chandra homomorphism that center acts. So the eigenvalue of center actually gives us something which is some polynomials, all actually polynomials which are symmetric with respect to shifted action of Weyl group. And then we use that to prove this formula. But this formula is actually a consequence of very beautiful result, which is called BGG resolution. So I would like to present it to you as well. So if you see somewhere this words, you know. Okay, and BGG is short for Bernstein-Gelfand-Gelfand. I always forget it's N or S, but you can check. Resolution. Is it N here? No. If somebody can Google. Is that N? I always forget. Sorry, resolution. Okay, so what is it? It is so let's formulate it as theorem. So let lambda be in P plus, then there exists okay, thank you. So there exists a long an exact sequence, so we resolve L lambda, finite dimensional reducible representation. It means that sequence starts like this. Then we know that there is homomorphism from M lambda. So now here we should like to write a kernel of this map. So exact means that kernel of this coincides with the image of the previous arrow. Okay. So therefore the kernel of this one is the image of M lambda. So this just says that this map is surjective, right? But then what is in the image of here should be in the kernel of this map, right? The kernel of this map, we almost hit this. It's the sum over mi's. And this mi's, I announced that we didn't see this in detail, but it's not hard to see. That each mi's are Verma modules. So here stays sum, direct sum. Inside Verma module, it's not direct. But here I would like to actually write direct. Si shifted action on lambda over I. So I can take direct, map it to M lambda, right, to each mi there that we figured out. But it might have some intersections, so image will not be direct already, right? So actually this map, it's not injective, right? Something glues together in here. So it also has some kernel, which I should write in here, and it always will be some direct sum of Verma modules. Okay, so I continue like this, and like some general term here is a sum over M W acting on shifted acting on lambda over all W in Weyl group, such that the length of W is K. So this is the first element of the sequence, and then second, and this is kth. And this is first. So length of Si is 1, right? Then I take everything that decomposes as SIs into two SIs. And this will be what goes next, right? So here are some dots. And then there's also some dots. Yeah, there's something of maximal length. So you have M. Sorry, let me. It seems it takes more place than I needed. Okay. So this I don't want to erase. So it's actually finite sequence. I take something of maximal length. Let's call it W0. It's on unique element, actually. And then it's 0. Okay. So this is a hard theorem to prove. You need to read additional book, I think, to do that. But it can be stated in the frames of our course, which is which says that it's a good result. It's hard to prove, but not hard to state. Okay. But why this implies this? Let's discuss that.
Sorry, what's the index of the first entry? W0.
Yes, W0 is the only element. It's 0 dot applied to lambda. Sorry, to lambda. It's the only element of maximal length. It actually takes C plus and maps it to negative C plus. So this element. It takes highest weight vector, goes to lowest weight vector. So that's what's going on. All right. So to see how it's related to the Weyl character formula, we just need the following lemma. So suppose there is an exact sequence of representations of G. So starts with 0, and then I have V1, V2, and so on. And then I have Vk, and then 0. And suppose that for each Vi, I can define weight. So in our case, it's just direct sum of representations of highest weight. Right, in BGG resolution as well. Okay, so then alternating sum over characters, so -1 to the I characters of Vi is 0. So this is, okay, let's see briefly why this is true. I don't know, maybe some people just familiar with just basic linear algebra, they just see it immediately. And it's kind of, it's basic. Okay, but why? So, of course, if I have sequence like this, exact sequence, I have similar sequence for weight subspaces, right? So, so we have for weight subspaces, I have V1 of lambda, V2 of lambda, and so on, Vk of lambda, and this goes to 0. Right? So therefore, dimension of Vk of lambda right, is dimension of Vk minus 1 of lambda minus, so this map is surjective, so I should subtract the dimension of the kernel of this map, right? So this is, let's call this map D, so this one will be D1, this is dk minus 1. Okay, so this is dimension of kernel of dk minus 1. But kernel of dk minus 1 is the image of Vk of dk minus 2, right? So this thing I can now rewrite as dimension of the image of Vk minus 2. right? This is just because the sequence is exact. The kernel equals image. But then dimension of image of k minus 2 is actually dimension of k minus 2, vk minus 2. Of course, I should everywhere put lambdas right here. Image with respect to a map k minus 2, dk minus 2, right? Minus the kernel of map dk minus 2. And then you just continue like that. So what we got? So dimension of vk is dimension of vk minus 1 minus dimension of vk minus 2. And then you just continue plus dimension of vk minus 3 and so on. And this is for each lambda. And it goes, and if you put all weight subspaces together, you will get corresponding alternating sum of characters. So, and so on. So therefore, let me write it here. So using this lemma, character of L lambda is, I'm using this, right? So I have sequence, exact sequence, and alternating sum is 0, right? So character of L lambda let me put on one side, and everything else alternating goes to the other side. So it is sum over negative 1 to the power L of W, right? So this each index here corresponds to the length, right? So each element of the sequence is indexed by the length of elements of Weyl group that I apply, right? So this is negative 1 that appears in here. Times characters of Verma module corresponding to W dot lambda. So this is just from this lemma in this sequence, right? But we know what is character of Verma module like this. So this is just negative 1 sum over W. So here also sum over W. Somebody wants me so much. Okay, maybe some bank wants me to have a credit or something. All right, so we have this. And then character is just E to the W shifted action on lambda, and then divided by this product, alpha in R plus 1 minus e to the negative alpha. It's exactly what's written over there. You can rewrite it in different forms and play with it, but this is basically what it is. Okay, so good place to stop.